Hello, everyone. Welcome to our pre-lecture 4. We're going to be talking about phase diagrams in this pre-lecture. Then as we get into class, we'll be starting chapter 11, looking at solutions. Okay, so a lot of what we've talked about after intermolecular forces in chapter 10 are basically phase transitions. And so going between solids and gases, gases and liquids, liquids and solids. And of course, last class, we spent a lot of time talking about these terms as well as understanding the quantitative nature of how we would quantify the energy going between phases or heating gases or liquids or solids. And so this pre-lecture and the end of chapter 10 that we'll be talking about, we'll be looking at phase diagrams. And so these phase diagrams consist of basically making measurements of substances for boiling or condensation points or melting and freezing points. And if we make them across a wide range, then we can create a phase diagram. And so these phase diagrams combine plots of pressure versus temperature for the liquid gas, solid liquid, and solid gas phase transitions, equilibria of a substance. These diagrams also indicate the physical states that exist under specific conditions of pressure and temperature. So for example, I were to give you a specific temperature of 200 degrees Kelvin and a pressure of 400 kilopascals, then you could locate that point on a phase transition chart and be able to tell me what phase something is. You can also look at the pressure dependence of phase transitions as well as the temperature dependence for all of the physical changes that a substance may undergo. And so that's what that means in text. With phase diagrams, I often think that it's best to just visualize them and graph them. And so on our x-axis here, we have temperature. On our y, we have pressure. And this is what a typical phase diagram might look like. And so any of the lines that we see along here represent a phase transition. And so, for example, if you start as a gas and you decrease the temperature over to this purple section, you would be undergoing condensation. If you started as a liquid and increased your temperature at this particular pressure, then you would, of course, vaporize your liquid and turn it into a gas. And so anytime you're crossing one of these boundaries, you are undergoing a phase change. There are a couple particular points, the critical point and the triple point, that we will also talk about here in a moment. Okay. And so again, just to put in text what I just said, that any line represents a phase transition that is associated with physical change, boiling, condensing, melting, and freezing. I should have also put sublimation and deposition there. Okay. The triple point is one of the points that was shown on that graph. It is the point on the graph where all three lines intersect and all three phases are in dynamic equilibrium at that point. And so an example of that would be shown with this GIF here with a chemical called cyclohexane. And so at this particular temperature and pressure that are achieved in this flask here, the chemical is in equilibrium between a solid, a liquid, and a gas. So you see that it's boiling there, and as it's boiling, it freezes. That's because we are in, again, equilibrium between solid, liquid, and gas at this particular temperature and pressure. And so when you hit this exact right ratio of temperature and pressure, then you're able to reach this triple point. Right. Another important point to consider is the critical point on the graph. So that would be this point shown for this particular CO2 phase diagram shown here. And another thing I would point out for a substance like carbon dioxide, if we think about it at typical pressure that we would experience at about sea level, which is about 100 kilopascals there, You would notice that if we were to just raise the temperature starting from minus 100 degrees Celsius, if we just raise that temperature going across at a standard, at the same pressure, you would notice that we'd never be able to reach a liquid phase. So this is another way to illustrate that carbon dioxide is something that in its solid form, which we would call dry ice, it would sublime to form carbon dioxide gas and never go through a liquid phase. That's of course what makes dry ice dry. Okay. And another point of interest here would be the critical point. This is, again, would be illustrated as this point right here. It is the point where a liquid and gas have intermediate properties, so that would be intermediate physical properties between the two, and we cannot distinguish between them being a gas and a liquid. And so we have a different name for that. We would call it a supercritical fluid. And above that critical point temperature, so above this point, the gas can no longer be liquefied no matter how much pressure is applied. Although you, again, get sort of this intermediate state between a gas and a liquid that we would call a supercritical fluid. And there's actually a really cool application for carbon dioxide as a supercritical fluid. It's used in the decaffeination of coffee and tea. It's also used to remove the grease and clean paper money. So anytime you have kind of an old grimy dollar bill, for example, if it were to be sent back to a mint for cleaning, they could clean it by putting it in basically a pressurized tank with carbon dioxide that they could turn into the supercritical fluid. That's a great non-polar liquid that would pull off all the grease from that dollar bill. And then once they drain the tank, then they would just release the pressure. The CO2 would, of course, turn back into a gas at that point, and you would just be left with grease. Or in the case of decaffeination, you would be left with caffeine crystals. I've taken a tour of, I don't know if any of you have heard the brand Celestial Seasonings. They're a tea company. And something interesting I learned on that tour was that when they decaffeinate their tea, they use this supercritical CO2. And the caffeine that they produce from their tea leaves that they decaffeinate, they can actually sell to an energy drink company. And so if you ever see energy drinks that say contain supplements, natural supplements from tea, what they're really saying there is the caffeine, or at least some of the caffeine we put into this energy drink came from tea originally, and we're going to call it a supplement. So it's just something to watch out for if you're an energy drink consumer. If you're looking for energy drinks that have tea supplements, in all likelihood, that just means they got their caffeine from tea. Okay. There's also a link if you would actually like to see someone decaffeinate coffee. There's a link to a YouTube video there as well. Okay. Great, that's it for this pre-lecture. We'll be starting chapter 11 in class, so I hope this was beneficial to you. And Avogadro says, have a great day. If you have any questions, please let me know. Otherwise, I will see you in class or in office hours. Take care.